Welcome to this introduction to intensified imaging. How to extract valuable information out of just a few emitted photons? Historically, image intensification based on intensifier tubes was the only way. Presently, this is no longer the case. When there are few photons to capture, electron multiplication CCD and more recently, scientific CMOS have become the methods of choice. These newer technologies come with some advantages, ranging from image quality and resolution to easy handling. But intensification is still useful if photons have to be detected in an extraordinary short exposure time of a few nanoseconds. EMCCD and CMOS cannot cover this range. Image intensifiers allow such extremely short exposure times, a capability which is often referred to as gating. So the question is, how can light be intensified? Image intensifier tubes use a loop wave for their intensification job. They convert photons into electrons, amplify the electron signal, and finally reconvert the electrons back into a photonic signal. To achieve this, an image intensifier tube consists of three main functional components: a photocathode, a microchannel plate, and a phosphor screen. So let's have a look onto this principal drawing. An object is imaged by a lens onto a photocathode. This is a thin layer of a special material which can convert photons into free electrons. The underlying physical principle is the external photoelectric effect. Albert Einstein was awarded with the Nobel Prize in 1921 for explaining it. After the electrons have left the photocathode, they are driven by an electrostatic voltage into the tiny tubes of the MCP. Tiny means here just a few microns in diameter. MCP channels are slightly tilted, not visible in this drawing, but this geometric detail is important for the MCP function, as it causes every electron to hit the inner wall of such a microchannel once it has entered it. There is a certain bias applied between the input and the output of the MCP. So the electron is accelerated, collects more kinetic energy, and therefore frees a couple of secondary electrons on every impact on the wall. The accelerated secondary electrons do the same, which finally results in an avalanche effect. A cloud of many electrons leaves the MCP output. The electrons are further accelerated before they hit the phosphor. Here, on the phosphor, the reconversion of fast electrons into many visible photons finally takes place. So we have amplified a weak image on the photocathode input into a strong image on the phosphor output. To finally get a digital image from the phosphor screen, we need an optical coupling, which can be a lens system or a fiber optical taper, and a digital camera module. It can be CCD or a CMOS camera. That's it. Let's take our new pco.dicam C1 intensified camera system as a state-of-the-art example for an intensified CMOS camera. Inside a solid metal housing, we have an image intensifier, a special, we call it tandem lens system for efficient optical coupling, and last but not least, a high-performance CMOS camera module capable of more than 100 frames per second at 4 megapixel resolution and 16-bit digitization. Here we are. The front end hosts the optical input. You can mount almost any manual lens as well as many motorized lenses which can be remotely controlled. The input lens focuses the image onto the photocathode of the image intensifier tube, and from here the intensification process starts as described before. Our user interface to the CMOS camera, where we can retrieve the images, is here at the back end. The data interface is CameraLink HS based on 10G hardware. It's a standardized and scalable high-speed camera interface capable of transferring more than 1 GB per second image data. A big advantage of CameraLink HS, it's all optical. A multi- or single-mode fiber connects to the grabber card of the PC, which can be hundreds of meters away. What else do we have? In most applications, such a special camera needs a tight synchronization with the experimental setup, pulsed lasers and stuff like that. To allow for this, we have here, with these B and C plugs, the possibility to connect a number of I/O signals. There is a trigger input to start the image capture with an electrical TTL signal. We have an exposure out signal where the camera indicates when it is actually exposing, and many more. We know the basics, so let's switch it on and take some images. This is CamWare, my control software for the Intensified camera system. It allows me to configure all relevant imaging parameters here on the right-hand side. We can select the exposure time. We can insert delay if necessary, and we can configure the pixel resolution and get in turn the maximum frame rate corresponding to this resolution. This histogram gives me an indication about the signal strength. I can see the distribution of the measured gray values across the full 16-bit dynamic range, and there is an indication for the average value. And most important, the function, the display of the images in this preview window. What is the key configuration parameter for such a recording? The exposure time, of course. It's an intensified camera system, so we can challenge it a bit. We'll choose 1 microsecond exposure time, which should limit the number of photons for the image construction substantially. There is no extra light source around. We have to live with the ambient light in this room. So let me press the record button. Oh, yes, this is an image. But why does it look like this? So grainy, so noisy. The image intensifier shows us effects of quantum statistics we are not used to see in everyday life. The light emission of almost every light source follows a so-called Poisson distribution, which means that even an absolute stable light source does not emit constantly the same number of photons at any time. Take a hypothetical light source which emits 10 photons per second as an average. 1 second, it's 9 photons. The next second, it could be 12. A measure for this behavior, we call it shot noise, is the standard deviation of the distribution of measured photon numbers. It gives us the typical discrepancy between the mean value and the actually measured value. Sounds complicated? The good thing is that for a Poisson distribution, we don't have to measure this standard deviation for every light situation. We can easily calculate it if we know the mean signal. The rule is simple. To get the standard deviation, take the square root of the mean signal. How can this help us understanding what we see? Let's do the calculation for our 10-photon example. We assume a constant linear gain of 100 times. So the meaning is, for each photon entering the image intensifier, 100 photons are output at the opposite end. So going back to our 10 photons example, the linear constant intensifier gain produces a signal of 1000 photons at the output. Now we have to have a look at the photonic shot noise behavior we have explained before. The 10 photons input signal is attributed with a photonic shot noise of round about 3 photons root mean square. These 3 photons are also linear amplified by a factor of 100. What is the result? Now the photonic shot noise attributed is around about 300 photons root mean square. What would we have expected? We have a 1000 photon signal. We only would have expected 32 photons RMS for a non-intensified signal. What is the consequence? In both cases, the root mean noise relative to the signal is 30%. So what we see? Intensified images show bright signals with an unusual high noise amplitude. Now it becomes clear. Intensified imaging like this is typically working with just a few photons, say 10, with the square root being 3. What we see in this image and considered as noise is actually the deviation from the mean value, and it is 30% of the signal. Approximately a third of the signal is shot noise. Let's compare this with normal, non-intensified imaging, where we typically deal with, say, 10,000 photons. Photons show a photonic shot noise of 100 photons RMS, and this is only 1% of the signal. And this 1% is almost not noticeable for the human eye. Maybe I can convince you that this noisy appearance of intensified images is really mainly shot noise. In other words, it's physics that we can't change. And it's not due to a poor camera system. Let me try the following. As always, if you can repeat the measurement, do it and improve the precision of your result by averaging. Here, I will reduce the shot noise by averaging images. Fortunately, the DICAM C1 is not only a fast camera in the sense that it can do nanosecond exposure times. It's also pretty fast in repeating this many times per second. With the possible 165 frames per second at this configured 2 megapixel resolution, I can put in, for instance, a 32 times averaging. This is done here. And I will still get 5 updates per second. Let's do it. Watch now the image quality. Although the mean signal is still the same, the images are much less grainy. We have, to a certain extent, averaged out the shot noise. I can even further improve the image quality, making use of the huge dynamic range the camera offers. Up to now, we have used only a small portion of it, about 2,000 or 3,000 counts out of more than 65,000 possible counts. Why not extend the exposure time to, say, 20 microseconds? The signal will be 20 times larger, but should still fit into the dynamic capabilities of this camera without risking saturation. I have to adapt the contrast of my display. And now watch the image quality. Even intensified cameras can produce good quality images if we put in more photons and/or use averaging. But of course, averaging and long exposure times are not realistic for this application, for which the camera system is built for, and where it outperforms all other imaging technologies. As said in the intro, we need this camera when ultra-short and precise exposure times of a few nanoseconds are requested, what we call gating. To give you an impression of what it could look like, I have prepared a simple experiment. This is an EM testing device, which can produce small discharge sparks driven by 15 kilovolts. Our visual perception will cheat us. Believe me, it's a very short event. It all happens in less than 1 microsecond. I'm curious. I want to get a 4 nanosecond snapshot of that spark. To align both, the 4 nanosecond exposure and the ultra-fast spark, I need to synchronize the two. As the discharge is non-deterministic, it only depends on how close I approach the 15 kilovolt tip to the ground anode. I will use the discharge itself to trigger the camera. How? The discharge comes along with the emission of an electromagnetic pulse. With a simple cable loop, which acts here as a receiving antenna, I can pick up this EM pulse, convert it within this black box into a proper TTL pulse, and tell the camera via external triggering, now make your 4 nanosecond exposure and capture the image. The camera is configured to externally triggered image capture. I only have to press the record button to arm it. This is what we get. It's also a good example that ultra-fast imaging does not necessarily mean to just dealing with a few photons. In the center of the spark, I have even reached saturation, 65,000 grayscales. A valid question would be, do I actually have to lock me so tight to the EM pulse? We can check it out. Put in a short extra delay between the arrival of the trigger pulse and the start of the 4 nanosecond exposure time, say 500 nanoseconds. Press again the record button and repeat the experiment. My preview window stays dark. 500 nanoseconds later is too late. I completely missed the event. It's actually fast. Okay, enough for a jump start into intensified imaging, and enough for now. More details coming soon. The basic functional group is always DICAM C1 channel. We can group it into a C4 system, one optical input divided up equally to 4 individual channels, and even, but this is perspective, C8. 8 channels coupled to one optical input gives you the chance to acquire 8 images in less than 1 microsecond. So intensified systems lost a bit of their application scenarios during the past 20 years with the introduction of EMCCD and CMOS technology, but there is still, I would call it, a strong niche for ultra high-speed applications where we need a proper gating. Gating means if I put in a 4 nanosecond exposure, I cut out all the light which comes before and after the 4 nanoseconds. That is what we call gating, and intensified systems are the only technology which can provide us with this functionality. So in respect of intensified systems, I would say replacing the traditional CCDs inside intensified cameras by state-of-the-art CMOS opens up the door to high-performance imaging in terms of resolution, 4 megapixel, speed, more than 100 frames per second, and of course sensitivity. So it's now much easier to retrieve the light information from the phosphor with a CMOS system because it has almost no readout noise, it has a high quantum efficiency, and we benefit from this all in the new DICAM C1.